Recordings rolling is. All right, we're back. So it's Monday, March 3rd. We're gonna pick up the review where we left off back last week. You guys have your notes out, right? Guys, everybody's got their notes out? All right, do I need to walk around and give some of you guys paper? All right, here. Get you guys some paper here. Okay, here, you guys got phones away, phones away. You guys are learning. All right, everybody's got phones away, got some notes out.
I got a pair of open ones. 10 minutes. We'll go outside the wrapper about.
All right, so you guys got papers for notes because we're picking out where we left off last week. Oh, you guys know SATs come up in a few days, so point out some things on your Google Classroom to help you out here. If you look back to last week, I posted you guys an Excel page shows where everybody's testing. Okay, most of you guys are testing. A lot of you guys are going to be relocating because there's going to be testing in this room. So, of course, there's going to be no physics on Thursday because we'll be testing you here. Right, there's a volunteer hours opportunity got from admin. So if you need that, you got some dates there. Oh, and over the weekend, I got the updated book of posters there. So that's all on Google Classroom for you guys. All right there. All right. And then, so I think probably a pretty good format for this week is just keep doing review like we've been doing, just get as far as I can get. Because I know a lot of you guys, a lot of your minds are probably on this SAT coming up. Okay. I think what I want to do next week is give you guys some in-class review quizzes and have you guys do those in teams. That's sort of the idea I'm kicking around right now. So probably look for that. Give you guys a week heads up. All right. So I remember last week we were onto this Unit 2 dynamics, but AP actually this year they're putting a ton of stuff in Unit 2. Right, so they're putting Newton's laws and forces. They're also including gravitation and orbits and some circular motion. So it's a ton of stuff, but it's going to go in order of what I have here. All right. So last week we did review Newton's laws of motion. You guys know Newton's 3 laws of motion right here. We were talking about acceleration being this bridge variable between kinematic motion and dynamics. And you guys have an example in your notes back on Friday. I was saying, well, if you kick a soccer ball with some force for some time interval, how fast does it leave your foot? Well, if you know the force acting on the mass of the soccer ball, you can get the acceleration of the soccer ball. And if you know the time interval that your foot is in contact with the ball, it's like a fraction of a second, right? And the ball starts from rest, you can navigate one of these kinematic formulas and figure out how fast it leaves. Right. And so I've seen AP ask plenty of those types of questions. I've seen FRQs that are involve this process right here. And you can go the other way too. Like if you know how fast the ball leaves your foot, you can back calculate, well, what's the average force on it while you're kicking it. So it's all there. You guys are looking at, all right, so springs, you can stretch or compress a spring, and the amount of force you put on it is proportional to how much it stretches or compresses. Okay. Also proportional to how stiff is the spring. That's the spring constant. Okay. Now, guys, there's a, you know what? I'm thinking right now, I'm thinking of 3 main formulas that apply to springs. And students mix up these 3 formulas all the time with the applications. So here, got a blank paper. See, I'm going to write spring formulas. Okay. And maybe you guys remember these or say like what categories of ideas you can talk about with springs. Guys, what's one formula related to springs? Huh? Okay, so I'm hearing 1/2 kx squared. Now, guys, if you say 1/2 kx squared, that refers to what property of a spring? Yeah, spring potential energy. So potential energy in a spring. Okay. So this is an energy idea. And guys, energy is measured in what? Joules. So if you plug in some number of meters here and some newton per meter here, yeah, it gives you some number of joules. This would also be the work done. So let me write work. Okay. Done to either stretch or compress the spring. Okay, same idea. Okay. What's another formula related to springs? Yeah. F equals kx. Okay. Where F of course stands for some force, and force is measured in newtons. Okay. Actually, both of these are on this graph, but the different properties of the graph, right? So coordinates, we're talking about Hooke's law, F equals kx. right? In the area of the curve, that green looking triangle is, well, the work done stretching pressing, the energy stored in the springs. Okay. Some textbooks throw a negative on Hooke's law to talk about the restoring force, because there's actually two forces here, right? There's the application force and there's the reactive force. And then more recently, like this semester, you guys learned a third formula for springs, which was what? Aha, yeah, the time period of oscillation, right? D pi times the square root of m over k. Here, I have to draw a picture for this one. So this could be like maybe a mass is on a spring, k, something like that. Yeah, this is time period of oscillation, which could be in seconds, okay, something like that. Okay. I think it was last year that this was actually the experimental design free response question. They said, how can you figure out the spring constant of a spring? And you have the spring, you have some masses, and you have a stopwatch, but you do not have access to a ruler. Okay? Yeah, you guys follow that? You do not have access to a ruler. So they were trying to navigate everybody towards this formula. And this is all they were given credit for. And I had some students that said, oh, Hooke's law, F equals kx. And I could just hang the masses, hang the weights and see how much does it stretch. Except they were not accepting that as an answer because you were not allowed to use a ruler or meter stick. You were only allowed to use a stopwatch. So that's all of this right here. Okay. Oh, guys, speaking of time period, what is 1 over time period called? Frequency. Aha. So that there could be a time in there too, right? That could be. Right. So you guys have like how frequently does it bob up and down? Like if it starts at the top and goes all the way down, all the way back up, that took some amount of time, t. The reciprocal of that could be frequency in hertz. Like how frequently is it? Boing, 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 boing. Is it like 3 times per second, 4 times per second? Oh, 3 hertz, 4 hertz. Right. We got here. We're looking at some free body diagrams. You guys told me last week. Rocket deep space constant velocity. Well, there would be no forces necessary, right? It's just going. Voyager spacecraft, here's an example. And this is the very last one you guys saw back on Friday. Air hockey puck at constant velocity across the table. Notice there's no horizontal forces. Now, maybe when you were hitting it with a puck, yeah, there was a horizontal force then, but that's in the past at this point. And air hockey puck is just going. Constant velocity means there's no forces, there's no net forces in that direction. Okay. So the only forces are vertical, it's weight, the air density. Okay. All right. So are we good? We're good. All right. So here's what I think should be pretty straightforward. Suppose I got a spring scale and I'm dragging a block horizontally across the table. Okay, so go ahead and draw the free body diagram for that scenario. I think everybody's going to get this right. Okay. And label all the forces. So that scenario right there. You're pulling block. Yeah. Which one? All right, so everybody got this free body diagram. Yeah. Well, constant velocity, right? Constant velocity. Okay. Looks like a lot of you guys got it. Guys, when you see constant velocity, what do you know is the acceleration? 0. Therefore, what is the net force? 0. So when you drew your free body diagram, you have 0 net force, correct? 0 net force. Okay. So here's 5 put together. Okay. So you're gonna have a weight. You're gonna have the normal force from the table holding it up. Okay, so those two definitely zero out vertically. Okay. The horizontal forces also have to zero out. If you're pulling a block across the table, I mean, that sounds like a force, like an applied force. You can label this F sub pull, F sub applied, F sub spring. AP would accept all those. Okay. But you have to cancel it out for this condition here for constant velocity. Okay, so you guys see how the net force is zero, everything cancels. Okay. Now, there's some property between this block and this table. Like maybe this block is made of wood and the table's made out of aluminum, whatever the materials are. It has to do with this coefficient of friction here. Oh, yeah.
If it cancels that one, then that means it goes nowhere.
If it started at rest, it would be static and it would be stuck to the table. That's true. Right. So the question is, if all the forces cancel out, wouldn't it just be sitting at rest? And it would be true if this friction was static friction. Okay. But if you break that initial static friction and you get it moving, okay, and now we're that condition, right? So constant velocity. Okay. You guys remember Newton's second law of motion? Actually, here, split back a few posters here. Okay. Here's Newton's second law of motion right here. If you have zero net force, guys, does zero net force mean zero velocity? No, it means zero acceleration, right? Zero acceleration. So if you're already in motion, you're just not changing how you're moving. Okay, just constant velocity. Okay. Yeah, it's the same thing as this rocket here, right? There's zero net force. It can be in motion, right? The Voyager spacecraft is in motion. It's just not speeding up or slowing down. Yeah. All right. So right. Now, depending on what information you have, you can figure out the values of these. Like if you're told the coefficient of friction, and okay, let's say you know the weight of the block, and therefore you very quickly know the normal force because they just bounce out. Okay. If you know what the coefficient of friction is, let's say it's like 0.5, then this friction force has to be half of this normal force. Wouldn't that be true for 0.5 coefficient of friction? And therefore you can figure out exactly how hard you have to pull it for this whole condition play out. Okay. Or alternatively, if you measure directly on the spring scale how hard you're pulling it, you can calculate what is the coefficient of friction. Okay. Yeah.
If the coefficient of friction is half, isn't the friction force 2 times? Or is it...
The friction force would be half of the normal force. Okay. If the friction force is like 5 newtons and the normal force is 10 newtons, that would be 1/2. Okay. Yeah. Okay. All right. All right. So you guys get there? Okay. Here's some common coefficients of friction. Like again, once you know what the material is, it becomes determinable. Like steel and aluminum. Like these are pretty set known numbers. Right? Now wood and wood, it's actually a little bit ambiguous because there's different kinds of wood and different ways you can cut the wood and whatnot. But here's kind of like ballpark numbers. Okay? And down here at the bottom, I gave you guys for tires on different kinds of road. Right? Is the road icy or wet or dry? Right? That could be just good information to know. And even these numbers aren't exact. Like this number 0.9, it can go bigger than 1, which may mean it's actually easier to lift a car up than it is to push it across the pavement. Right? That can happen. Right? All right. This next one, we're gonna do a derivation here. All right, so car brakes to stop. Now, way later on, I have an energy version of car brakes to stop, having to do with braking distance. All right, this one, I want you guys to figure out what is the acceleration. Okay, so guys, derive this from scratch. Oh, and somewhere in the mix in the answer is going to be a coefficient of friction. Here, I'll spell this out. So derive, well, I'll say the negative acceleration. That might commonly be known as deceleration. Deceleration of car braking to a stop. And the coefficient of friction is part of the answer. Okay. Now, is it, okay, while you guys are driving that, okay, is it kinetic friction or static friction? Well, it could be either one, depending on, do you guys remember we talking about anti-lock braking system? Right, anti-lock braking, right? So I remember when I got my license, that was part of what I had to learn about. So if it's kinetic friction, that means that the tires are squealing across the road, like, right, like they're actually sliding across the road. If it's static friction, then that means that the tires are rotating forward a little bit so that they are not sliding across the surface of the road. Okay? And guys, which of those scenarios will the car come to a stop sooner? The kinetic case or the static case? The static case, where the tire's actually rolling forward a little bit. Now, in modern day cars, just go ahead and slam the gas pedal, or sorry, the wrong one, the brake pedal. Go ahead and slam the brake pedal, and the computer system will automatically take over and will automatically know how to rotate the tires forward to bring you to a stop in a hurry. Okay, so okay, so it looks like Alex got it, I think Hector got it, I think Landon got it. Alright. He's working on, okay, yeah, some of you guys are working on it. Getting there. Okay. Alright, so you guys are trying to figure out how quickly can that car brake to a stop? Right, what is the acceleration or the deceleration of the car? Close, that's close to the answer. Okay.
Yeah.
Alright, then can you drive the whole thing? Alright, so what's a good starting point? Maybe Newton's second law of motion. Okay. We're trying to figure out how much the car can brake to a stop. How much can it accelerate, decelerate? Okay. Which is going to come out of Newton's second law of motion. Okay. Well, if you look at this pre-body diagram I got set up for you guys, you can see what the net force is. Guys, what is the net force on that car? The friction force, right? Because the weight and the normal force is balanced out. Yeah, so the friction force is the net force that's causing the car to slow down. So that would, okay, so that would be that step, right? Friction force takes the place of the net force. Okay. Oh, but if you think back to like this here, same idea. This friction force, isn't this just coefficient of friction times the normal force? Right? No, that would really be true if it's kinetic friction. If it's static, it's allowed to go up to that point. So I would say, well, if we're talking about like the maximum possible deceleration sort of, okay, I would just go ahead and call this equals for that case. Okay, if you want to figure out how much can a car slow to a stop. Okay. So in place of friction force, you're going to do what times what? Yeah, coefficient of friction times normal force. Okay. Yeah, which coefficient of friction is it? Well, it depends whether or not you have anti-lock braking in your car. Okay. If you're driving a car from the 70s. What's the next substitution? Yeah, normal force is equivalent to mg, and that's because some of the vertical forces goes to zero, right? The car is not accelerating up or down. So I'm going to replace this normal force with mg, and the reason for doing that is that now on both sides you have the mass of the car. What happens to the mass of the car? It cancels, and there's your answer right there. Okay, so the most that a car can slow down is take your coefficient of friction. For example, here. Okay, so for example, suppose you were on a dry road, and let's say you have anti-lock braking, so you're allowed to take advantage of static. So you got this 0.9. Right? You guys see 0.9? Okay. Notice I'm just saying 0.9. That has no units on it. Or I could say Newton per Newton. Say 0.9. So take this 0.9, pop it right there. And then for the gravity field of the planet matters. For Earth, let's round that to 10 meters per second squared. Put it all together. What would the acceleration be? Yeah, 9 meters per second squared. Okay, that's how much the car could brake to a stop. That's also the maximum value the car could speed up starting from rest, especially like in a drag race or something. Start from rest and then light turn screen, sort of take off as fast as you can. Right? I mean, it maxes out that way too. Right? Car's got to pushing at something. Oh yeah. Yeah. That would be a great extension question. Oh, suppose you want to figure out how fast is the car building up to, like a velocity question, because I don't see anything about velocity on this page. Okay? So the tie-in is you have to go back to, where'd my kinematic formulas go? I always have them right behind me. Well, here, let me dig up some real fast. Kinematic formulas. Here's some kinematic formulas right here. Okay, so once you have acceleration, if you want to know how fast is the car going, you have to know something else. Now, let's say the car is starting from rest. Guys, could V not be zero? Car starts from rest.
Yeah.
And you guys just found the acceleration. You said mu times g, so you have that. So if you want to figure out how fast the car is building up to, you have to know either what or what. Aha! Either how far is the car gone distance, or how much time has passed. Right? You guys ever hear like, oh, this car will go from 0 to 60 miles an hour in 8 seconds. Well, that's from 0 to 60 miles an hour in 8 seconds. There's a way you can calculate acceleration from that sort of weird units, but that's the idea. Okay. All right. So you guys got that. This next one, oh, I know is a military entrance question. Suppose there's a plane flying at constant velocity through the sky. Can you guys draw a free body diagram for a plane at constant velocity? Plane at constant velocity. Yeah, free body diagram. Yeah, free body diagram. Yeah. If you go military, there's a good chance they're gonna say, what are the forces on the plane at constant velocity? And you say, all right, what's one force you guys came up with? Okay, drag force. All right, what else you guys came up with? Lift. What else? Weight. And what else? Thrust. Aha. All right, so there's your basic 4 forces. Oh, now for constant velocity, if you got this right, does the forward force and the backward force cancel out? Yep. And does the lift force and the weight cancel out? Yep. All right. You guys see that? Each cancel out along those axes, right? Okay. Now, speaking of this drag force, you're only going to have this drag force if the plane is facing air drag, which it will be. Now, that's something that you don't see too much in this class. So here, maybe I'll script these a little faster. Okay. So normally in this class we ignore air drag, so free fall would just be its own weight, and it would be accelerating at free fall, G, A equals G. Okay.
Will that ever tell us like something to get constant velocity and the velocity is 0? Like it turns out to be 0, like.
Oh, well, I've never seen them do something like that. Yeah, if they say something's moving at constant velocity, and then it turns out it's at rest, I've never seen them do that. No. All right. Now, guys, what do you know about terminal velocity? That means.
I don't.
Oh. Yeah. Okay. Yeah. There you go. So it's going so fast that the drag force builds up so much that there's 0 net force. Right? So it's moving really fast. It's just not speeding up anymore. Okay. But you only get this if there actually is air drag, right? Like this cannot happen in a vacuum, right? Okay. Now, between this picture on the left and this picture on the right, well, there's a transition. So maybe like this middle picture is like drag force building up. Okay. That drag force, by the way, is proportional to the speed squared. So if you double the speed, you can get 4 times the drag force and so on. Right? Triple the speed, 9 times the drag force. Okay. It also depends on all this other thing. Okay. Remember doing engineering classes in college? I saw this formula pop up a few times. Actually, there's slightly different versions of this formula too. So depending on what you're working with, but and then actually, I want to see if you guys can put this next one together. So let's bring in drag force. Let's say you drop a ball off a cliff. I want to know what's the speed of the ball as a function of time. Well, let's consider that there is air drag. In fact, let's say there's so much air drag, or maybe this cliff is so tall rather, that at some point this ball is going to reach terminal velocity before it hits the ground. Right, can you guys figure out what that graph would look like? Velocity versus time with air drag. Oh, yeah.
Sorry, we're starting. Oh, it's just V versus T, right? So it's like.
Yeah, okay, right there. Okay. Yeah, let's see. Let me guys get this. Yeah. All right. Yeah.
Terminal velocity, it needs time to speed up.
Right. Yeah. Okay. So, okay, guys. First, let's go back and review. What if there was no air drag? Let's go way back to last week. Guys, remember if there's no air drag, it just looks like this.
Yeah.
Guys, remember that? Right. So X versus T, V versus T, A versus T. 0.0 is the top of the whole deal. Right. So yeah, you drop it, it starts at 0 meters per second. And it picks up at 9.8 meters per second squared. That's the slope of this line. Now, if you include air drag, then at the moment you release it, isn't it actually pretty close to this? Maybe like for the first couple of seconds, it's probably pretty close to this anyway. Okay. But it doesn't stay like that because it eventually is going to reach terminal velocity, which is not shown on this graph. Okay. So yeah, walking around, a bunch of guys, looks like got it. And came up with that right there. That's what you're looking for. Right there. Ooh, this next one. Block in equilibrium on incline. Okay. Now, you guys know what equilibrium means. The net force is 0, which is 0 acceleration. Okay. The block might be at rest if it's a static situation. It might be sliding at constant velocity if it's kinetic. Okay. And the free body diagram that you guys are drawing right now could apply to either of those situations. And if you didn't know if it was static or kinetic friction, you wouldn't actually know just by looking at this free body diagram. Is the block at rest or is it sliding at constant velocity? All right, who's going to get this free body diagram?
Oh, this
Throw some ideas at you guys. If AP says draw only forces, not components, how many forces should you be drawing on that block? Three? 3 forces? Okay. Now, okay, guys, after you get the 3 forces, go ahead and take one of those forces and break it into dashed components. Can you guys do that? Okay. And you guys probably know which one I'm talking about, right? So 2 of the forces leave in place, 2 of the forces that are already perpendicular to each other. Okay. But one force, let's say the weight, right? Can you guys break the weight into components and dash those components? Yeah. Yeah, that'd be a force. Okay. All right. Yeah, looks pretty good. That is it. That is it. All right. Boom, boom, boom. Pretty close. Like that. Okay. All right. I think some of you guys are getting this. Some of you guys are pretty close. Yeah, that looks like it. That is. I'll just see here. Okay, yeah. That could be it. That could be it. All right. I think a lot of you guys get this. All right, pretty good. Pretty good. Okay, so here's what you're looking for. Looking for the weight is straight down. The normal force is, well, normal to the surface. That's what normal is, perpendicular. And the friction force is parallel to the surface. Okay? So it looks like this blue normal force and this red friction force are perpendicular to each other. Okay? And usually how you want to think about these incline problems is introduce a Cartesian coordinate that is, or a Cartesian system that runs parallel and perpendicular to the surface. And now these red and blue vectors are already aligned to that. But the weight, I would have to break into these dashed components to make more sense of it. Okay? So notice that I dash them. I definitely dash these so that I'm conveying to whoever's interpreting this that I'm not double counting the vectors. Right? So I'm just re-representing it. And do you guys need to, walking around the room, looks like you guys were pretty good at this, is actually making these parallel and perpendicular to the surface. Like especially this one here. Like students usually miss this one all the time. They have it like going like parallel to the ground. But a lot of guys have this actually parallel to the surface, which is just what I'm looking for. Okay. Okay, so this angle is this angle. If this is 29 degrees, this is 29 degrees. Yep, the same angle. Oh, and then mg can break down to mg sine theta and mg cosine theta. Oh, yeah.
Good question. So I
Yeah.
know that we don't include the components because it double counts to mg. But what if we don't include the mg and then include the components?
Okay, yeah, so what if the question is, what if you did not put mg at all, but you just drew the 2 components, right? I think AP would not give you credit for that because I've seen them use this phrase over and over and over. They say draw the forces, not the components. So the fact that they always specify that doesn't mean they're actually, this is what they're grading. They're just looking for that, right? And then if you went ahead and dash components, they usually just go ahead and let that go. As long as you dash them, right? You just have to have dash, right? Okay. Now, if you got everything exactly proportionally correct, then you guys see how this is mg cosine theta? The normal force is also equivalent to that. Like if I measure how long this is, let's say on my paper, this is like 8 centimeters long about, and this is also like the same 8 centimeters. Okay. And how about this friction force? Now, for equilibrium, this would be true, is this mg sine theta would be equivalent to the friction force, wouldn't it? Okay. So on my paper, looks like it's about 4 centimeters long. This one's about 4 centimeters long. Is that? Okay. Oh, guys, speaking of which, if these proportions are correct, if this is 4 centimeters, this is 8 centimeters, that might correspond to like 4 newtons versus 8 newtons. Who can tell me what could be the coefficient of friction between these two objects? 0.5. Right? That's like 4 over 8. Right? If everything's proportional. Right? Right. Now, guys, what if you change this angle theta? Here. What if theta was 0 degrees? If theta is 0 degrees, what's the normal force exactly equal to? Yeah, the weight. Right? So the normal force would be 100% of the weight. And then as this theta gets bigger, 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 what happens to the normal force? It gets smaller. And what if theta goes to 90 degrees? What is normal force approach? 0. Okay. You guys basically just told me this right here. Okay. So that's all I'm doing is I'm just looking at the relationship between the weight and the normal force for a changing angle. Okay. So this angle goes up. Okay. All right. Now, let's have a 0 friction. Oh, whoops. All right, wrong. Okay, I gave you guys the answer. Oops, I didn't need to do that. Okay. So, guys, if there's 0 friction, how is this free body diagram different than the ones you guys just drew in your notes? No friction. Do you guys see there's only 2 forces on this? There's only 2 forces, the weight and the normal force. That's it. That's it. Okay. Now notice this could be moving either direction. It doesn't matter if it's sliding up or down the incline, right? Doesn't matter. The free body diagram would be the same. All this math over here would be the same. Okay? And this math leads to what is the acceleration? Now the acceleration is always going to be downhill. Right? If it's already moving that way, then it's speeding up. If it's kind of moving uphill, say if you gave an air hockey puck a little push and now it's sliding uphill, it would be slowing down because it's still accelerating kind of downhill. Okay? Okay. So net force on mass. The net force, you guys see what the net force is? This is mg sine theta is the net force. Right? Acting on block mass m, the m, cancel, g sine theta. Okay. Your Garcis's carbon incline lab was basically this, right? Carbon incline. I know there's little wheels on it, but it's basically a frictionless type situation here. You can approximate that. Okay. All right. You guys ready for the next one? All right. This next one's harder. This next one is, what if there, okay, oh, look, friction's back. Friction's back. Now there's friction. In fact, my free body diagram looks like the one that's in your notes from a couple minutes ago. Right? So it's still equilibrium. Yep, constant velocity. That's an example of equilibrium. Okay? From this one, I want to see who can derive, and I can see this being an FRQ, who can derive the coefficient of friction as a function of, well, let's say any or all other variables there. Guys, go ahead and solve for a coefficient of friction. This was actually a lab you guys did. So while you guys are working on that one, and this goes back a few months ago, how'd you guys figure out what's the coefficient of friction between 2 surfaces? And I had you guys use 2 different methods. Okay, so one method was you guys just use a flat horizontal table, kind of like earlier in class today, right? If you use a spring scale and drag a block across a horizontal surface, right? That was one method that you could compare the drag force to the weight force and divide those 2 to get coefficient of friction. This was the other method. I think I remember some of you guys setting up a textbook and then lifting the textbook at some angle, right? You guys had a protractor, you get how many degrees, okay? And at some angle, whatever weight you had would break friction and slide down. Now, the breaking friction part is more of a static question, and the sliding at constant velocity is more of a kinetic question. Okay? But they weren't too far different from each other anyway. Right? So, can you solve what is the coefficient of friction? I think a lot of you guys are on the right track, I think. Yeah. Here, a lot of you guys, the handwriting is a little bit small, so I may have missed, some of you guys got the right answer. Oh, some of you guys may have got it. Guys, show of hands, who thinks they know the answer to this question? Mu equals what? Who knows the answer? What you got? Tan theta? Yeah, tan theta, right? Okay, Jack's saying tan theta, right? Is that what you guys are getting to? Mu is tan theta? Yeah, okay, I'm seeing, yeah. Some of you guys are nodding, saying, yeah, tan theta. Okay. So let's see, how could you start this out? What do you guys think is maybe a good first step? Right, okay, well, here's what I got set up here. I know constant velocity is zero acceleration, therefore zero net force. Okay, now if there's zero net force, maybe this mg sine theta and this friction force would have to zero out. Okay, is that what I have next? Yeah, that's exactly what I have next. All right, so you subtract the two, this one and this one, subtract them, and that has to zero out. Okay. Now, since I have a friction force here, how can I substitute in coefficient of friction? Yeah, coefficient of friction times normal force. That would be the substitution for that, wouldn't it? Coefficient of friction times normal force. Okay, so rearrange that. There it is right there. Coefficient of friction times normal force takes the place of friction force. Okay. And I think there's still one more substitution I gotta have, which is what am I thinking of?
Normal force.
Yeah, this normal force is your mg cosine theta, right? There it is, right there. Okay. Yeah, is everybody okay with every step along the way so far? Okay. Okay. Now at the very end here, what cancels? Mg. Okay. And then what is sine theta divided by cosine theta? Tan theta. Aha, there it is. That's the answer. Okay. So if the block is sliding at constant velocity, yeah, this would represent coefficient of kinetic friction. You could tweak this a little bit. If you said what angle does it initially break the friction and begin sliding, that would give you static coefficient of static friction. Okay. Yes. Very good. All right, guys, good. Guys, good. All right. You guys remember chain gang? So which of these spring scales is reading the most force? Yeah, one on the top, because it has to hold up all the weight below it. Right, like barrel of monkeys. This monkey has to hold all the monkeys beneath it, all the monkey brains. Okay. Versus if you're at the bottom, you only have to hold them underneath you. Okay. Guys, there's a variation on this. If I just turn this horizontal, do you guys remember questions that had to do with like trains? Right, trains. Okay, so would it be true like the engine has to pull all the cars behind it? Okay. But as you get towards the back, there'd be less and less force to pull the cars behind those. Right. Now that's as long as the train is accelerating, that would be true. Guys, what if the train's going at constant velocity? Then would there even be any force at all? No, because now they're all just moving because of inertia. So constant velocity, there'd be no force at all. But if the train is accelerating, then yeah, the front link has a lot of tension force, and then there's successively less and less and less force on the way back. Okay. I've seen here. Here's a question I like, or AP likes to ask too. Is sometimes they'll have like a box and a rope. Like some different size box, and maybe there's like a box on top of it, and there's like another rope, and they'll tell you like this tension FT1, and maybe they'll ask what is this tension FT2. They'll tell you like M1, M2, M3. Seen AP ask those kinds of questions. That's just a more complicated version of what starts from this. Ooh, here. You guys remember like hanging lantern questions? So if there's say a lantern of some known weight, and you know these angles alpha and beta, can you solve for the tensions and the supporting ropes? Right, you guys remember that question? Right. So now this might take a few minutes to solve. We played around class. I guess you could, but here's the guiding principle. You could set up a system of equations. You guys see a blue equation and a green equation here. Here, it's really a system of equations. Right? And the blue equation says that the horizontal components cancel out. So, if you know, actually, maybe you don't yet know either of these forces. Suppose that's a setup. Maybe you don't know the tensions in either of these yet. I don't know the tensions. So this unknown tension times cosine of alpha, which is right here, and this unknown tension times cosine of beta, well, those would have to subtract to zero, right? Those zero up. And then vertically, this left tension sine alpha and this right tension sine beta have to cancel out with this weight pulling down, and that's the setup right here. Is that now you would have then at that point you have two equations with two unknowns. The two unknowns being what are the two tensions? Say if you know alpha, you know beta, and you know the weight, you just wouldn't know the two tensions. Can you guys solve two equations, two unknowns? You guys do that? Okay. I think I told you guys too. The SAT coming up in a few days. I've seen lots and lots of systems of equations. Okay. And you guys know I uploaded the review videos to Google Classroom too, right? For my other classes. Okay, so if you want a good review there, okay, lots of systems of equations. This next one. Let's have an upward accelerating elevator. Now, guys, if the elevator is accelerating upward and you're standing inside on a scale, does that scale read more than your usual weight or less than your usual weight? More than. So normally you weigh 100 pounds. Here, this might feel like 120 pounds, right? And you would feel heavy, right? But really, that scale is reading the normal force, not actually Earth pulling on you, but the normal force. Those are mismatched. Okay. Now, you guys see the answer down here. Normal force ends up being m times g plus a. That might be a good equation to pull out of your back pocket for a multiple choice, but not necessarily a free response question where they would want you to derive this from scratch. So go ahead, guys, derive this whole thing so that here's the answer right here. Okay. Normal force reading on the scale is m times g plus a. Can you derive that from scratch? There's a good chance you're going to be asked that question right there. And if it shows up on an FRQ, you got to derive it. While you guys are driving that, this could also refer to the tension force in the cable pulling up the whole elevator, right? If the mass represented the entire elevator with everything in it. So you guys see what's implied in the answer is, and if you'd be solving for the normal force, maybe you could know M, you can know G, and you could also know A. Maybe this could be given values, right? I guess if you know any three of these, you could solve for the fourth one, but this is set up in such a way where it looks like, say you know M, G, and A, right? Okay.
Oh,
Guys, what's maybe one good starting point? What's a good starting point? Newton's second law. Aha, Newton's second law. If you see masses and accelerations, it's probably going to fit into Newton's second law at some point. Yeah, okay, I think I'll do it. Yeah. All right. So we got here. There's Newton's second law of motion. Net force is mass times acceleration. Now, guys, the net force is the difference between these two, isn't it? Okay. The normal force up minus the weight down would be the net force. Okay, so net force is ma. Net force is also the difference between those two. So put it all together. Bam, looks like that. Now all I gotta do is add over the mg, and then factor out the m, and it looks exactly like what shows right there. Like that. All right, you guys good on that one? How about what if the elevator was accelerating downward? How would this final expression change a little bit? Yeah, this would be g minus a in here, wouldn't it? Yeah, sure would be. Okay. And what about this? Guys, what if the elevator is moving up really fast at constant velocity? What can you say about the normal force? It's right, yeah, equal to your own weight. Right. Yeah, and the net force would be 0. Yeah, that's true. All right, so here you go. Here's 3 scenarios: accelerating down, accelerating up, and in the middle is equilibrium, which might be at rest or it might be constant velocity. If you're inside the elevator, then during a single moment, can you feel the difference between being at rest or being at constant velocity?
No.
Nope, you have no idea inside the elevator. You have no idea. Okay. Kind of like we're on a giant spinning Earth right now. We don't really feel it spinning because we're all moving together at sort of a constant velocity. Ooh, Atwoods. I think we did some Atwoods actually last week, but see if you guys can derive this from scratch. So I want you guys to figure out, well, here, maybe I'll, do we have like a minute left here? Yeah, okay. You know what I should do is I should give you guys a couple of masses, have you guys figure out what is the acceleration of the system if I throw some numbers at this. And also, what is the tension force in the connecting string? But yeah, those going to ring pretty soon here. So that's going to be our pause point today.